Hi, do you know how fast electrons travel in a wire? Considering electricity travels close to the speed of light, when you make a phone call, your voice reaches the other side of the planet almost instantly. With a click of a button, the Nigerian prince has your credit card information in a snap. Well, let's calculate. I cut 1 centimeter length of this 22 gauge wire. I calculated that in this tiny piece of wire there is roughly around 280 million trillion copper atoms, assuming that it's pure copper. You can check my calculation sheet in the description. Every copper atom has one loosely held electron that can be pushed around to create electric current, and the charge of one electron is around minus 1.6 times 10 to the power of minus 19 coulombs. Very small. Charge of one electron times their number means there is around 44 coulombs worth of electron charge in the wire ready to move and create electric current, which are held by the same number of protons, and the wire is electrically neutral. Now imagine we want to run 1 amp of current through this tiny piece of wire. 1 amp is a lot of current. It can kill you instantly and can run like 100 Tamagotchi games to entertain a bunch of losers. No offense. Current in ampere is the amount of charge in coulomb passing per second. So 1 amp of current is 1 coulomb of charge passing per second. Considering we have 44 coulomb of charge in that 1 centimeter piece of wire, the speed of charges would be 1 over 44 centimeter per second, or only 0.23 millimeters per second. It's so slow. It's a speed like this. Now life makes much more sense. I was always wondering in a battery how all those electrolyte ions and chemicals stuck in a boogery goo can carry electric current. They can't mechanically move fast. But now I know they don't need to move fast to carry massive amount of current. Then how does electricity move close to the speed of light? It's not the electrons that move that fast, it's the wave between them. For example, if I hit this piece of stick with a hammer to hit that glass, the shock waves will travel at a speed of... The shock wave moves at a speed of wave in a stick and gets to the other side almost instantly, while the particles themselves only move a little bit forward. Similarly, if you shove one electron into a wire, the electrons repel each other and the electric wave travels close to the speed of light, and one electron will drop out of the other side almost instantly. But let's see what happens if we change the thickness of the wire. If a wire is very thin, it is still tons thicker than your penis. Sorry. Anyway, in a thinner wire, we have less available charges to move. So to create 1 amp, the 1 coulomb would have to move faster. Because the same amount of charge that would pass a spot in 1 second is spread out over a thinner wire, but still has to pass in 1 second. Imagine these two magnets are two copper atoms stuck in their springy crystal, and this magnet is an electron passing through. The passing electron has to move through the electric fields of the atoms, and it shakes them too. There needs to be some energy per charge or voltage to force the electron through the fields of the atoms. And if you want to move faster, you need even more voltage, and the atoms vibrate even more. What is this vibration of atoms? It's what we feel as temperature. Atoms vibrating is heat. The more they vibrate, the hotter they are. The faster the electrons pass through them, the more vibration they create, and the hotter the wire gets. Is that animated enough? That's why running the same current through a thinner wire creates more heat. We need more energy to move electrons faster through those pesky electric fields of the atoms, so we need a higher voltage. Different atoms hold their electrons with different force. For example, in iron, we need a higher energy to move the electron. Ow! Ow! We need a higher energy to move the electrons through a stronger field, and the motion of electrons creates more vibration and heat. It is as if the conductive material show resistance against the motion of charges. Resistance! And that's what resistance is. All these pesky electric fields not letting electron to move through freely and wasting energy in form of heat by vibrating atoms. And so the resistance of a conductor was defined by Georg Simon Ohm as the amount of voltage or energy per charge required to create a certain amount of current through the conductor, or voltage divided by amp. And that's the Ohm law, and Ohm is the unit of resistance, which is also shown by omega. We can also show it as voltage equals to resistance times current. So if we want more current for the same resistance, we need to increase the voltage. Any component made to resist is called a resistor and is shown with this symbol. I guess because the charge would have a hard time flowing through these wiggly lines. The actual resistors could be made as through-hole components like this one, which means that these pins have to go through a board and the color stripes indicate the resistance. Or they can be made as these tiny surface mount components that solder right onto the surface of the board, or other types like panel mount. I know how to read these color bands and I suggest you search the web and learn it too. It would help you find a through-hole resistor easier through a pile. Doesn't quite help you with the surface mount ones though, but you can always get a meter and measure the value and make sure. But there is an engineering way they typically use to show the values, which also applies to capacitors and inductors and such. If you see a few digits like XYZ, the last digit is the number of zeros that would go in front of the first digits to make a complete number. For example, if you see 1103, it means that there are 3 zeros in front of 110 to get 110,000. In case of resistors, this is 110 kilo ohm. In case of surface mount components, if there is room, they just print this number directly on the package. But in case of through-hole components, they just color code these numbers. For example, these would be brown, brown, black, orange. The resistance is calculated by this formula. Oh, right, you find a way I say formula funny, huh? How do you say it? Formula. Formula. It's formula. So, the resistance is equal to some constant which is called the specific electrical resistivity and depends on the type of material like iron, aluminum, copper, or whatever, times the length of the wire divided by the area of cross-section of wire. It is simple. For a specific material, the longer the length of the wire is, the more electric fields the charges would have to go through, which makes it harder and so higher resistance. And also, the thinner the wire is, like I said before, for the same current, the charges would have to go faster, which means it's harder and again more resistance. It's like the flow of water. Right now I have a certain pressure and flow from this hose. If I make its output thinner, the water would have to flow faster under the same pressure, which is harder too. And if I add some length of hose to it, the flow is even slower as the water has to overcome the friction against the pipe. The cup at the center seems to be feeling faster, but it's not. The high-speed jet is pushing the water up and out. For example, I have a 10 ohm resistor, and if I put 10 volt across it, there will be 1 amp through it. Oh, it's burning now. Which brings us to the subject of power. Too much power through a resistor and it will burn like you saw. Every component has a specific continuous power rating. For example, the one burned was 1/4 watt and this one can handle 50 watts. But every component can handle more power than its rating for a short period of time. See here, I have a new 10 ohm resistor and if I apply 10 volt across it momentarily, it will remain unharmed. And that's how I survived the incident. A bit longer and I would have been cooked like this resistor. Be careful around electronics, kids. We know that power is the amount of energy spent in a given time, which is also equal to energy divided by charge times charge divided by time. And if we look carefully, this is just voltage times current. So we know power is equal to voltage times current, and from Ohm's law we have voltage is equal to resistance times current. So we can calculate power to be equal to voltage squared divided by resistance, or resistance times current squared. There's a whole bunch of other stuff to talk about around resistors, but for now squeeze this information into your heads and we will talk about them later. And I will probably make an unlisted problem solving video around what we just talked about so it sticks into your tiny brains better, and leave the link in the description below. Research! Oh, and I know that these 101 series are more boring than my normal videos, but I think they serve a good purpose. I really appreciate your likes and the support of my channel at patreon.com. You're helping me power through making these videos and helping with the school giveaways, making everyone smarter. And in return, patrons are always included in any draw, and also there are some special other perks. Thank you.